Mesdames, Messieurs les membres du jury, honorable assistance, bonjour et soyez les bienvenus. My name is Chiraz Rezzaz and today I will be presenting my thesis on using Kolmogorov-Arnold methods to investigate knowledge graphs for embedding, link prediction and query answering. This work was carried out under the supervision of Professor Barra and Dr. Alba. Here is an overview of the main sections of this presentation. We will begin with an introduction, followed by the problematic. Then I will walk you through the state-of-the-art, introduce the proposed approach, and walk you through the implementation, results, conclusion, and finally the future perspectives. Knowledge graphs represent structured relationships between entities and are widely used in diverse domains. One important task in such graphs is link prediction, which involves predicting missing or potential connections between the entities. The core question we seek to answer is, can Kolmogorov-Arnold networks improve the performance of knowledge graph embeddings, particularly in terms of link prediction over knowledge graphs? In this section, we will examine existing approaches that include multilayer perceptrons, graph neural networks, Kolmogorov-Arnold networks, and key concepts in knowledge graph embeddings. Let's start with multilayer perceptrons, or MLPs, one of the foundational models in neural architectures. MLPs are inspired by biological neurons, where each neuron in the network receives input, processes them, and produces an output that can trigger the next layer of neurons. This layer structure allows MLPs to mimic the way biological neurons process the information. MLPs have three main parts: the input layer, one or more hidden layers, and the output layer. The input layer receives the raw data, which is then passed through the hidden layers. Each hidden layer consists of neurons that are connected to every neuron from the previous layer. These challenges show the need for models that are designed to work with complex graph data. This leads us to graph neural networks, which improve MLPs by tackling their limitations and leveraging their strengths. Graph neural networks, or GNNs, are a class of neural networks which are specifically designed to process graph-structured data. Unlike traditional neural networks, GNNs operate on graphs made up of nodes or vertices representing relationships and edges representing relationships. GNNs use a process called message passing, where at each layer, nodes update their feature by aggregating information from their neighbors. GNNs come in several types, each designed to address specific graph analysis tasks. These variations adapt the general framework of message passing to suit different problem domains. So first we have graph convolutional networks, or GCNs, which extend convolution principle from grid-based data, and the Arnold-Lehmann graph isomorphism test. And they consist of the sum of the features of a node and its neighbors, and they are suited for graph-level tasks like prediction. And finally, we have graph attention networks, or GITs. As their name shows it, they introduce an attention mechanism to GNNs by assigning weights to the neighbors, and they are suited for tasks where nodes relations vary in importance. While GNNs have achieved success in handling graph-structured data, they inherit many limitations from the MLPs they rely on. First, we have the lack of interpretability, since they are often black box models. Over-smoothing, there is a reduced model's expressiveness. They deal with the problem with scalability when we have larger graphs. And the neurons can scale in lows, which means there is a disproportionality between the model size and the accuracy we achieve from it. Kolmogorov-Arnold networks are designed to overcome these issues. Unlike traditional MLPs, which use fixed activation functions at the nodes, Kolmogorov-Arnold networks, or CANs, use learnable activation functions on the edges, the hidden layers, and the output layer. Each input is passed through a series of univariate functions. Here are the univariate functions. These functions act as learnable plan-based activations associated with each edge in the graph. The results from these functions are then summed in each node, and we can express a can as a composition of its different layers. By aggregating features from neighboring nodes, applying linear transformations, and using a nonlinear function like ReLU, KAGCN enhances this process by replacing the linear transformation and ReLU function with a single can layer. A knowledge graph is a structured way of representing information from real world using a graph. In a knowledge graph, nodes usually represent entities of interest, and edges represent the relationships between them. One of the key tasks in such graphs is link prediction, which aims to infer missing links by predicting whether a relationship between two entities exists. A knowledge graph is typically composed of triples of the form HRT, where H, the head entity, represents the subject of the relationship, R, the relation is the type of connection, and T, the tail entity, is the object of the relationship. Their symbolic nature makes them difficult to use in deep learning models. Knowledge graph embeddings handles this problem by embedding the entities and relations into a continuous vector space to preserve the semantic and the structure of the information. There are various KGE models that use different scoring functions to evaluate the plausibility of triples. These models can be divided into three categories. So first we have the distance-based models, where the relations are modeled as vector translations, rotations, or transformations. The second category is the semantic matching-based models, where the relations are measured through a semantic matching score. And finally, we have neural network-based models, or deep learning models, which learn the complex interaction between entities and relations. So let's dive into the proposed approach. Traditional KGE models embed entities and into vectors and relations depending on the model into vectors, matrices, or tensors. Then a scoring function is defined to assign higher scores to true triples and lower scores to incorrect or unlikely ones. Training starts with negative sampling, where we generate false triples to contrast with true ones. Then we optimize a loss function to give higher scores to correct triples and lower scores to incorrect ones. So our approach builds upon traditional KGE models, enhancing them with graph-based reasoning by introducing a GCN. So first, our model starts by defining the entity and relation embeddings. Then our entity embeddings will be refined with the GCN, which aggregates information and data from neighboring nodes. And then we use these updated entity embeddings with the original relation embeddings to score our triples. This way, this model captures both semantic model we proposed, it's the KAGCN model. So here we just replace the GCN model with the KAGCN model. For the implementation, here are the datasets we use. They are knowledge graphs. So the UMLS and the nations datasets are smaller datasets, and the WN18RR is a larger one. Three key metrics: mean rank, which measures the average position of correct answers. The smaller it is, the better the model performs. We also used mean reciprocal rank, or MRR, which focuses on the rank of the first correct result. The higher it is, the better the model performs. And finally, hits at K, which counts how many positive triples are ranked in the top K positions against a bunch of corrupted negatives. The higher it is, the better the model performs. We also tracked execution time per epoch. which is essential for assessing computational cost. And we define the best model according to the average of MRR, hits at 1, hits at 3, and hits at 10. So here is why we chose the Tucker model. First, Tucker was chosen for its expressiveness, enabling it to model all relation types. Its parameters stay efficient even when we have growing entities and relations. Its shared tensor helps with multitask learning, enabling it to achieve a stronger performance. And finally, Tucker is a generalization of several previous models. Here are the tools we used for the training. We used Python as the programming language, Google Colab and Jupyter Hub to train our different models, and we kept track of the results in Excel sheets. And here are the libraries we used for the training. PyTorch is the foundational deep learning library which was used for neural network models. PyTorch Geometric is PyTorch based and is used for graph machine learning. Random to keep track of the randomness. Can to introduce our can layers. Time to keep the execution time. Pykin to train our baseline models to compare with the results, and NumPy for numerical computation and tensor manipulation. So now here are the results. We will start with the results on the UMS dataset. So as we can see, our models outperformed the Tucker model and all the state-of-the-art models. So for the Tucker plus GCN, it achieves the best hits at 1 and MRR results. And the Tucker plus KA-GCN further improves these results for hits at 3, hits at 10, and MR. Then here are the results for the nation's datasets. This time also our models outperformed all the state-of-the-art models, especially our Tucker plus GCN, which, as we can see, achieved 100% score for the hits at 10, and the best results for hits at 1, hits at 10, MR and MRR. And the Tucker plus KA-GCN had very strong results also and had the best hits at 3. And finally, here is the last data set. This time, as we can see, the Quat model is the one having the best performance on every metric except for the MR. Our model Tucker plus GCN gave competitive results and gave for the hits at 3, hits at 10, and MRR the third best results. On the other hand, the Tucker plus KA-GCN model produced mixed outcomes. It obtained the lowest MR, which means that its ranking is very efficient, but it was not as effective as other models on the rest of the metrics.